Hello guys and welcome to PLC Goods online video tutorial. In this video we are going to learn the bit and word shift instructions, the sequencer instructions, and we will do a project. The shift and sequencer instructions are grouped as file shift sequencer. Let's start with BSL and BSR instructions. BSR is short form of bit shift right. This instruction needs a word address, for example B30. The address should be started with a sharp sign. It means the inserted address is important, not its stored value. Obviously, the B30 address refers to here and it includes 16 bits. Then we need an address from the control data file. So let's double click on the R6 control file. The first address of this file includes some status bits such as enable done and error and two numbers in these two addresses. We already learned some of them when we were learning timer and counter instructions. A PLC recognizes a current state of a BSR instruction with these data. The len address stores the number which is entered in the length field of a BSR instructions. Let's use the first address of the control data file R60. Note that you can increase them if you need more addresses. Here, I should write a Boolean address which its state is important to us. As an example, let's enter the address of my second digital input, I1. Finally, I should write a positive integer number, for example 20. I will explain the length field later. Now let me use an open contact to enable the BSR instruction. Now let's test this simple program on computer to understand how does a BSR instruction work. Let's open the binary and input data tables. Here I have referred to B30 address and entered number 20 as the length parameter. This means I have selected 20 bits of the binary data file, starting from the first bit of B30. Therefore, I have selected all 16 bits inside the B30 address and also the next 4 bits of B31. Based on the program, BSR instruction can be activated by the first digital input. By the first activation, a PLC copies the state of this address I1 to the 20th bit of the selected bits. By the next activation, first all 20 bits will be shifted to the right side and again the state of I1 will be copied to the 20th bit. Now let me change the state of this bit to 0 and activate the BSR instruction. The BSR instruction shifts all 20 bits to the right side by each activation and it copies the state of this address to the 20th bit. I hope you have learned how does a BSR instruction work. The BSL instruction works similarly, but in the opposite direction. It shifts all selected bits to the left side. Now let's explain what FFL and FFU instructions are. The LFL and LFU instruction work similarly. FFL is a short form of first input first output load. This instruction needs a word address for its source field. Let's use N710 address. I should write a word address here. Let's use N70. As I mentioned earlier, the sharp sign means the inserted address is important, not its stored value. The instruction needs to use an address from the control data file. Finally, let me type 6 as the length parameter. Let me define a suitable symbol for this address. Besides the FFL instruction for loading data, the FFU instruction is used for unloading. So let me use a FFU instruction in the second round. Pay attention to the addresses. First, I used R60 address for the control field of FFL and FFU instructions. Let's use a new address N711 for the destination field. All parameters of FFL and FFU instructions are the same, except the source field of FFL instruction and the destination field of the FFU instruction. Pay attention for both of the instructions. I used the N70 address as the FIFO address and number 6 as the length parameter. So these 6 addresses are selected by the both instructions. Now when I activate the FFL instruction, it loads the source value into the next available position in the FIFO array, and the FFU instruction unloads data from the 6 selected addresses to the N711 address. Now let's test the program. Let's open the integer and input data tables. Now let's enable FFL instruction. The PLC loaded the source value into the first address N70. Let me change the source value and activate the FFL instruction again. Note that the PLC transferred the new value into the second address N71. Let's change the source value and activate the FFL instruction again. PLC has loaded the source value to the third address N72. I can continue the loading process until the 6 selected addresses are used. After that, the FFL instruction won't work. FFL instruction has filled the 6 selected addresses. Right now, it cannot load any new data. Now, let's enable the FFU instruction. This instruction unloads data to the destination address N711. Note that the FFU works inversely. By the first activation, it unloads number 10, which was loaded as the first number. By the second activation, the PLC transfers the second number 25 to N711. This slide shows how FFL and FFU instructions work. FFL loads data into a part of memory which we call that a stack, and FFU unloads data from the stack memory to a specific address. The source address determines which number should be loaded into a stack. This address determines the first location of the stack memory, and the length parameter determines the number of elements that the stack memory needs to store data. The FFU parameters function similar to the FFL ones. Note that a destination parameter determines the destination address for an unloading data. Overall, the FFL instruction loads data to a stack memory, and FFU unloads them from the stack memory to a specific address. Pay attention. The first input data will be the first output data. Similarly, the LFL instruction loads data on the stack memory, and the LFU unloads them from the stack to a specific address. Pay attention. When LFL and LFU instructions are used, the last input data will be the first output data. Now we are going to learn sequencer instructions, and I will do a simple project. Let's learn the functionality of sequencer instructions by defining and doing a simple project. We need to generate a program to control traffic in two directions, west to east and north to south. Each way has one traffic light. The program should control 6 lights with 6 digital outputs. Let's use the 6 first bits of O0 output address. I have connected the green light of the west to east path to the 6 digital output. Similarly, I have to activate this bit of an output address to turn on the red light of the north to south traffic light. There are 4 states for the 6 digital outputs to control the intersections, which should be repeated in steps 1 to 4 sequences. After the last step, the sequence should be started from step 1 again. The condition of each step can be stored on a word address of a PLC memory. I used 4 addresses of a binary file to store a state of 6 digital outputs of each step, words B31 to B34. Now I can use a SQO instruction to move the first word, a start condition, to an output. So all outputs will be 0 or off based on the B30 address. Then a SQO instruction can transfer steps 1, 2, 3, and 4 to output address O0 to repeat the sequence. For example, in step 4, a PLC activates these bits of an output address. Note that the SQO instruction does not determine the state of all 16 bits of O0 address. It only controls the first 6 digital outputs. Bits 6 to 15 of O0 are available but not used here. Therefore, to prevent the SQO instruction to transfer these bits to an output word, I can use a mask word. Based on a mask word, a SQO instruction only moves bits 0 to 5 from a PLC memory to an output address. Other bits won't be controlled by a SQO instruction because these bits of a mask word are all 0. In consequence, these bits of a PLC outputs are available but not used in this project. Now let's write the program. These are the sequencer instructions. First, let's add a sequencer output instruction SQO to the program. The file parameter determines a starting address of a PLC memory which a PLC transfers to a destination address. This address should be started with a sharp sign. For this project, I need to write the B30 address. A mask word determines which bits should be transferred to a destination address. For this project, a SQO instruction needs to control the first 6 digital outputs. This is its binary value. It is equal to the number 63 in a decimal format or 3F in hexadecimal standard. I can use either of these representations of 63 as a mask value. RSLogix 500 uses H or B symbols to indicate if a number is a hexadecimal or a binary one. Decimal numbers are used without any indicator. A destination parameter is the address where the data is sent. My destination address is an output address to turn the lights on or off. A SQO instruction needs an address from a control data file. This address includes some status bits and 2 numbers. An enable bit indicates whether a SQO instruction is enabled or not. When a PLC transfers a last value of a selected data to a destination address, it sets a done bit to 1 as well. In this project, B34 address stores a last value. The position number indicates a current step that a PLC is going to send its data to a destination address. The length parameter determines the length of my data. It is equal to the number of steps. A PLC sets an error bit to 1 when it detects a negative number is entered as the position parameter or when a negative number or 0 is entered in the length field. Here I should enter the steps number of 4. The start address is B30, so this address is used to store an initial state and the length parameter which is 4. So the 4 next words will be used in this sequence B3 1 to B3 4. Here I can determine a startup address that it can be a number from 0 to 4. Let me insert a normally open contact and test the SQO instruction. Let's compile the program. This is an error. This message says unconfigured I/O address used because my digital outputs are placed on my PLC whose address is 0, not 1. I set my PLC address back to 0. Well, if I click on I/O configuration, I can see the address of my PLC is 0. So its digital outputs addresses start with 0, not 1. Now let's modify the data of the sequencer based on the light steps. The address starts from B30. Let's save the program and open it in RSLogix Emulate 500. Let's download and test the program. Let's select the Run mode. Let's open the input and output data tables. Now let's enable the sequencer instruction. Note that by each activation, the PLC sends a specified data to a selected address. Right now, the sequencer has reached step 3. By the next activation, the step 4 will be executed. Now, the sequencer reached the last step. The PLC has activated the done bit, and by the next activation, the sequencer will go back to step 1. At this point, let's learn other types of sequencer instructions. Sequencer compare compares its entered data with the value specified by a source parameter. If the selected data is equal to the source value, a PLC activates a found bit. SQL loads data from the source address to a sequencer file, so the SQL and SQO instructions work inversely. Now let me define and do a simple project. I wish to write a program to turn output LEDs on from the last LED to the first one and to repeat this sequence automatically. These are the output LEDs. I want to turn on the last LED, then the 10th LED until it gets to the first one. Then I want to repeat this sequence from the last LED automatically. This is the final program. I have used this SQO instruction, which is activated by the done bit of this on-delay timer. The start address of my data is B30 and this output address is my sequencer destination. So in step 1, this word will be copied to the output address. Based on this word, only the bit number 11 will be on. By the next activation, this word will be transferred to the output, so the 10th output will be on. This sequence will be continued to turn on the first output, and after that it will be repeated. Instead of using a simple contact, I have written this part of my program to start the sequencer automatically. It has two timers. Each timer activates another one. The preset parameter of both timers are equal to 1 second. I have used the done bit of the second timer to activate the sequencer instruction automatically. Let's download, change the PLC mode to run mode and test the program. Now let me activate the first digital input. Notice that each timer is activated for 1 second and the sequencer turns on each LED for 2 seconds. Let me magnify the screen to have a better view. I hope you have learned how to use shift and sequencer instructions. We will continue learning instructions, which can be divided into two groups: move and logical instructions and program control instructions. Then we will see how analog signals can be used in our programs. Finally, we will do a simple project to read and use a potentiometer's voltage. Let's start with the move and logical group of instructions. Here I have added a normally open contact, and now let's add a move instruction. This instruction moves the source value to the destination address entered inside the dest field. Now let me explain how the MVM instruction works. I should enter three addresses. Let's select them from the integer data file. Note that the third integer number is 0. Let's compile and test the program with RSLogix emulate 500. Let's change the PLC mode to run mode. If I enable the inserted MVM instruction, its destination value will change from 0 to 3. Do you know why? Let me open the integer data file. Alright, this is the source value which should be transferred to the destination address and the N71 address that it includes the mask value for the inserted MVM instruction. Right now only 3 bits of this word are equal to 1. So PLC moved only 3 bits, bit numbers 0, 1 and 5 of the source value to the destination address. Note that this is the binary form of number 3. These are bitwise logical instructions. Let's insert and explain bitwise logical OR. This instruction needs 3 addresses as well as the MVM instruction. Now let's compile and test the program. I have opened the integer data file to see the numbers in binary format. We learned OR logic for 1 bit during the first videos. This instruction uses OR logic for all 16 bits of the bits specified by source A and source B and sends its result to the destination address. Other bitwise logical instruction works similarly. Now let's insert and test the clear instruction. This instruction needs only one address, like N72. If I activate the inserted clear instruction, it will reset its related address value to 0. Now let's see what the program control instructions are. First, let me add jump to label and label instructions to my previous program. The jump to label instruction is paired with the label instruction by using the same address for both. First, let's use a jump instruction in the first rung, which can be enabled by a normally open contact. The jump instruction causes a PLC to skip over some rungs. Here I must write a label. Labels start with the letter Q. Note that I am writing my program in file number 2, so the next number must be 2 and after a colon, a number from 0 to 999 should be entered. Now let me insert and use a label instruction in another rung with label Q20. Remark: for simplicity from now on, in reading out I/O terminal addresses or labels, I will only read out the I/O specifier and terminal number. Therefore, Q:0.0 I:0.0 Q2:0 and N7:2 I will read out as O0, I0, Q0 or N2 respectively. Let's compile and download the program to see how the jump and label instructions work. Obviously, PLC executes these 2 rungs. Let's change this number manually. Now let's enable the jump instruction. PLC skips over the second rung and executes its program after the label. Now PLC is not executing the second rung and the MVM instruction cannot change the stored value in its destination address N72, but the clear instruction can reset the N72 value to 0. Let's continue with these three instructions: jump to subroutine, return from subroutine, and subroutine label. First, let me tell you what a subroutine is. Pay attention. Until now, we wrote all our programs using the main file or file number 2. We can create another file and divide all programs into 2 or more parts. Then we can call each part of our programs from the main file. Now let me write a simple program inside the created file. First, I insert a subroutine label instruction. After that, I can write my program. Let me use a RET instruction or return from subroutine at the end of this run. Let's complete the program. Its logic is simple. Here, there is an error. The first rung does not have any output. Let's move the SPR instruction to the next rung and delete the first one. Now I want to call my new program, which was written inside the file number 3 from the main file. I need to modify my main program. Let's delete the last rung and use the jump to subroutine instruction instead of the jump to label. When PLC executes this instruction, a flow of program execution will jump to the beginning of the selected subroutine file. Here I should write my destination file number 3. Now let's download and test the program. Only this part of my program is executing. If I enable this contact, a flow of program execution will jump to the beginning of the selected subroutine file, and after that it resumes its execution from this point of my program. Now this program is called from the main program. So in the first run, this contact can activate this output. Another important point is about this instruction, return from subroutine. Obviously, I cannot activate the second output because of this RET instruction. Pay attention, PLC returns to the main program when it reaches a return or end instruction. Okay, until now, we have learned how to skip over a part of a program or define and call a specific subroutine. Now let me explain an instruction that we can use for program debugging. I have placed a TND or temporarily end instruction on the right side of the third rung. Now the processor executes the whole program from the first rung to the end coil on the right side of the last rung. If I activate the TND instruction, it stops the processor from executing the rest of the program. Then a PLC updates its physical inputs or outputs. It then restarts program execution from the first rung. So far, we have learned the basic instructions and features of RSLogix 500. Now let me explain how analog inputs or outputs can be used in a PLC program. At the beginning of this tutorial, I explained my PLC hardware and its wiring, and until now we did many projects with digital I/O ports. Digital sensors or push buttons have only two states, on or off. These instruments only use two voltage levels to send their states to a PLC. Also, we can use two voltage levels to turn on or off digital actuators such as this lamp. But there are many devices such as level transmitters, flow meters, and actuators which work with analog signals. For instance, a voltage between 0 and 10 volts. Other basic signals are minus 10 to 10 volts, 0 to 20 milliamps, 4 to 20 milliamps, and so on. Naturally, we need more than one bit, usually 16 bits, to store and process these signals in a PLC program. Let's see an example. Suppose there is a level transmitter to measure the level of a substance. This transmitter can be tuned to generate a voltage between 0 and 10 volts when the level of the substance is between 0 and 50 meters. PLC can receive this signal with its analog input module. My analog module model is 1769 IF4. These modules give us a number from 0 to 31,206 when they receive a voltage from 0 to 10 volts. But how we can use these numbers? Nowadays, we can find the user manual of each device on the internet easily. In this manual of Allen Bradley, I can find my analog input module properties. First, let's see its wiring diagram. I will use this diagram to connect a potentiometer to my analog module. Also, this module needs a 24-volt DC power supply to work. This is another wiring diagram. My module supports both analog current and voltage signals. This table shows that analog module has 4 channels to receive 4 analog signals. It needs a 16-bit word memory to store each signal's value. Words number 4 and 5 are used to show the states of each received signal. S0 to S3 bits will be 1 if there is a detected error in each received signal. These status bits show overflow and underflow states. Now let's see this table with the valid input table title. This table shows valid measurement ranges. For instance, I am going to use 0 to 10 volts DC. So my analog module will give me a number between 0 and 31,206 based on this section of the table. Note that in the PLC program, we can use math instructions to convert any received number to its equivalent voltage or level of the substance. Pay attention, analog output modules work inversely. PLC sends a number to an address of its analog output module to generate a suitable voltage or current. Now let's define and do a simple project. I want to develop a PLC program to read a voltage signal. I connected a potentiometer to the first channel of the second analog input module whose address is 2. The nominal voltage range is 0 to 10 volt DC. Also, I have used a voltmeter to display the input voltage and PLC to calculate the real voltage value. The program can use this formula to convert the received number to a number between 0 and 10. Also, if the voltage level is lower than 2.5 volts, PLC will turn on the green lamp. And if the voltage level is greater than 7.5 volts, PLC will turn on the red lamp. Let's see the program. First, I need to enable my analog input channel, which is wired to my potentiometer, which is connected to the first input channel. Here, I must select the channel signal type. Okay, my program's logic is simple. I have used division and multiplication instructions to get the input voltage from I to 0 address and calculate the real voltage according to this formula and save the result on F81. Then I have used less than and greater than in instructions to compare the calculated voltage on the F81 address with 2.5 and 7.5 to turn on the green or red lamps. Let's test the program. First, let's reduce the voltage. Obviously, when the voltage is lower than 2.5 volts, PLC turns on the green lamp. Now let's increase the voltage to turn the red lamp on. Okay, I hope you have learned how to use RSLogix to program the SLC 500 and MicroLogix PLCs, including the MicroLogix 1000, 1100, 1200, 1400, and 1500. In the next video, we will start learning RSLogix 5000 software to program the most powerful Allen Bradley PLCs, including the control logics and compact logics controllers. Thanks so much for watching this video.